So, today we are going to be discovering the Earth's geometry. Now, you might not think that we would need an entire class period to talk about the shape of the Earth, right? Except we do. And you'll see. Right now you're looking at a picture of the first, or at least a replica of the first globe that was ever made. And that was actually an ostrich egg model of the Earth. They believe that it's the first depiction of the New World because it dates back to about 1500 AD. It's believed to be from Florence, Italy, and they think that it's linked to Leonardo da Vinci. So remember, I talked last time about how scientists are creative, and lo and behold, this is one of those things. One of the things that people often talk about is the flat earth. And I know when I was in school, we used to learn that before Columbus sailed, or maybe even before Magellan sailed around the earth, that everybody thought the earth was flat. And that really just wasn't true. It's actually been known that the earth was round since the time of the ancient Greeks. It was Pythagoras who first proposed that the earth was round sometime around 500 BC or BCE, before the Common Era. Um, so why did he think that? Well, he reasoned that if the moon was round, then the earth must be round. Now, here's my question. Is that an observation or an inference? If he is reasoning that since the moon is round, the earth must be round, is he observing the roundness of the earth, or is he inferring it? Second, he saw the shape of the earth's shadow on the moon during an eclipse. Is that an observation or an inference? So, the shape of the earth's shadow on the moon was obviously round, and therefore he then concluded that, hey, yes, the earth itself is round. So a lot of the early thinking actually does not believe in a flat earth. So think back to what you learned probably in grade school. A lot of early travel was by ship. And one of the pieces of evidence that you could have to argue that the earth is round is that when a ship comes over the horizon, we don't just suddenly see the whole ship. You see the top of the ship first, and then the sails, and then the rest of the ship, because it's coming up over the curve of the earth. If the earth were flat, we would see the entire ship the entire time. So let's move ahead to Aristotle. In Aristotle's book called On the Heavens, he wrote, quote, again, our observations of the stars make it evident not only that the earth is circular, but also that it is a circle of no great size. For quite a small change of position to south or north causes a manifest alteration of the horizon. Right? Isn't that what you were thinking? In other words, we see different sets of stars in the night, really depending on where we are on the Earth. So the sky over the northern hemisphere where we are is not the same sky over the southern hemisphere in terms of what stars and constellations we see. So even back then, Aristotle knew if the Earth was flat, then we would all see the same stars at any given time, but we don't. So here is a picture of the lunar eclipse of 2001. So you can see right there the shape of the Earth's shadow on the moon. It's not always absolutely circular, simply because, the pictures kind of distort it, but you can see that it is certainly not a disc. There's not a line, there's not a flatness to it, there's a curve to the shadow. So, finally, what you are seeing right now is the, let me get my words out. This is the path that explorer Ferdinand Magellan took when he circumnavigated the Earth. Circumnavigate simply means to go all the way around. And if the Earth were flat, he certainly would not have been able to complete that. And so finally we know, because of Magellan's famous voyage, that yes, the Earth is certainly not flat. It is a sphere. So let's take a look at some of those facts, though. Let's look at some modern day evidence. So the first thing is gravity. How does gravity affect the shape of the Earth? Well, we know that gravity is basically a fundamental force of nature, and it influences so many processes within the Earth's interior and above its surface. It was over 300 years ago when Sir Isaac Newton explained the basic principles of gravitation and the concept that we know as a G-force, which is the force of gravity. So how does that deal with what we're talking about today? Well, as the Earth spins, it spins in a counterclockwise motion, and as it does that, the shape of it becomes slightly flattened. So it's not truly a sphere, it's more of an ellipsoid. And that simply means that it's a little bit flat at the top, a little bit flat at the bottom, and it kind of pooches out in the middle. Kind of like, somebody who's middle-aged. We've got a little bit more stuff in the middle than we used to have. What about circumference? How does circumference offer us facts on the shape of the Earth? Well, the circumference of the Earth is not going to be the same if we go from pole to pole, or if we go completely around the equator. Those aren't going to be the same if the Earth is spinning due to the force of gravity, and that gravity is pulling the top and the bottom towards the center, and so it's a little bit flat on top, a little bit flat on the bottom. The circumference is going to be different. It's going to be shorter around the poles, and it's going to be a little bit wider around the middle, around the equator. So, what is the true shape of the Earth? We call it an oblate spheroid. Make sure you remember that. The shape of the Earth is actually an oblate spheroid. Well, what is that? If you want to be technical, an oblate spheroid is a rotationally symmetric ellipsoid having a polar axis shorter than the diameter of the equatorial circle whose plane bisects it. What? What in the world did she just say? Here's an easier way to remember it. It's kind of a squished sphere. A little bit flat on the top and a little bit flat on the bottom, and it bulges out in the middle. So a squished sphere, not super squished, just a little squished. So why exactly is it that shape? What do you think affects its roundness? So oblateness. When we talk about oblateness, it just means how spherical an object is. And we actually give it a number. Oblateness has a number between 0 and 1. 0 is a perfect circle. That's easy to remember because when I think of the number 0, it looks, kind of like, I know it looks more like an oval, but I can remember that that is circular. And oblateness can go from 0 to the number 1. 1 is a straight line, correct? The number 1 is a straight line. Well, the oblateness of anything with a 1 is a straight line. So you can be anything between 0, which is a perfect sphere, and a 1, which is a perfectly straight line. And anything else is the decimal between those two. And it tells us how spherical an object is. So let's look at some quantitative observations. Here we have a table, and we have the planet. We have Venus, Earth, Saturn. We see the distance from the sun. All right, you see what we're looking at. And now look at the rotation period. We're going to compare these in Earth time and Earth days. So Venus, 1 day on Venus lasts 243 Earth days. So is it spinning very quickly? No, not at all. And what's its oblateness? Well, in this table it says that it's 0.00. So Venus is almost a perfect sphere. Well, according to this, it is a perfect sphere. Now let's look at the Earth. We're a little bit further away from the sun. Our rotation period is much faster. We rotate 1 time in 24 hours, so that's 1 day. And our oblateness is only 0.0034. So we are pretty close to a perfect sphere, but we're not. We're still a little bit squished. Well, let's look at Saturn. It rotates even faster. 1 day on Saturn is only 10.5 hours. And look, its oblateness is 0.098. So that's getting closer to a 1. It's still pretty far away, but it's getting closer to the number 1. So Saturn is more squished or more oblate than the Earth and Venus. So it looks like, if this were our evidence, to me that looks like the slower you rotate, the more perfect you are. And opposite that, the faster you rotate, like Saturn, the more squished you become. Okay, well, if all we had were those 3 pieces of evidence, I think that we'd be on to something. But I want you to see something else. What if we add Pluto? Pluto, 1 day on Pluto is 6.4 Earth days. So it's slower than the Earth and Saturn, but not by much. And then with Venus, it's way faster than Venus, but look at its oblateness. Pluto, based on this table, is a perfect sphere. So, our quantitative observations don't give us enough evidence to support what we might have originally thought, that the faster something rotated, the more oblate it was. I'm going to switch gears here for a minute, and I want to talk to you guys about more of investigating the facts. And I want us to back up and think about before NASA took pictures of the Earth, before we had GPS, before any of that, in 2000 BC or BCE, a man by the name of Eratosthenes actually measured the circumference of the Earth. To me, that is incredible. That is absolutely incredible. Let me tell you the story about this guy. So, he calculated it in 2000 BC within 1 degree of accuracy. So, Eratosthenes used Aristotle's idea that if the Earth was round and distant stars in the night sky would appear in different positions to observers at different latitudes. You know, and latitude is up and down as you move north or south, is what I should say. As you move north or south, you change your latitude. Well, Eratosthenes knew that on the first day of summer, every summer, the sun passed directly overhead in Syene, Egypt. And on that day, at the beginning of summer, at midday, he measured the angle of the sun from overhead in the city of Alexandria. And Alexandria was 5,000 stadia. That's just a unit of measurement they used. It was 5,000 stadia away from Syene. So, in Syene, he knew that at noon, the sun was directly overhead of a well. You know, like a well water. So he looked down in a well, and in Syene, it was directly overhead at midday. But when he traveled on the first day of summer, 5,000 stadia north to Alexandria, he found that there was a different angle that the sun had in the well up there. In fact, he realized that the displacement, or the different angle, was about 7.2 degrees. So, here we are, and he was using this math. He knew that there were 360 degrees in a circle, okay? Well, if you take the 7.2 degrees that was different from Syene to Alexandria, he said, okay, well, that's 1/50th of a circle. All you do is take 360 and divide it by 7.2. And that's 1/50th of a circle. Well, if you remember back to geometry, the ratio of that 1/50 is the same ratio as the distance between Syene and Alexandria. The ratio between that distance and the total distance around the Earth, or the circumference of the Earth. So the circumference, he theorized that the circumference could be estimated by multiplying the distance between the two cities. Remember I said that 5,000 stadia? So he multiplied that by 50, that 1/50th of a circle. And so he said, okay, well then, to get all the way around the Earth, it would be about 250,000 stadia. You're probably listening to this and thinking, She said she was going to tell us a story. We did not know it was going to be a math story. Well, I've got some more math for you. So let's take a look. Whoops. I suppose I should have clicked through that. All right. So this is the basic math he used. He went, let me see if I can draw this for you. He went from here at Syene and on that first day of summer, and everything lined up perfectly. And then when he went to Alexandria on the first day of summer, obviously the next year, he noticed that the direction to the sun at noon was about 0.2 degrees different from where the sun was in Syene. So now, I'd like for you guys to get out a sheet of paper and do the math with me. Or at least let's pretend like you are. I'm going to do it with you. Okay. So what is 1 stadia? Well, 1 stadia is actually 185 meters. And we all know that there are 360 degrees in a circle. And what they did, or what he did, was divide 360 by 7.2. And he got 50. So this is 1/50th of the circle, or the sphere, I should say. And that sphere is the Earth. So let's look at the distance between Syene and Alexandria. So 5,000 stadia. Now remember, for every 1 stadia, there are 150 meters. So we have 5,000 stadia times 150 meters per stadia. That means these cancel out, and you're left with meters. So 5,000 times 185, that'll give us 925,000 meters. Now, let's convert that to kilometers. By doing that, you simply divide by 1,000. And then that'll give us 925 kilometers. All right. So good? Good so far? So, that was the distance between Syene and Alexandria. Well, he knew that that distance was 1/50th the distance of the Earth. So all he had to do was calculate the 925 times 50. And so in today's calculations, we would get 46,250 kilometers. Look at that. You guys just calculated the circumference of the Earth. But wait, there's more. So, the actual circumference of the Earth is 40,008 kilometers. So boy, this guy was close for using a stick and some well water. That is amazing. But I want to give you a chance to earn some points. Sorry about that. I messed up the why was he wrong. So, I want you to think about this. Why was Eratosthenes' calculations not quite right? Why was his calculation larger than the actual circumference of the Earth? And remember, his was a polar circumference. He was measuring from pole to pole. How do I know that? Well, remember that Syene was south of Alexandria, and so he was going from Syene north to Alexandria. So Alexandria is north, Syene is south. He was going from, he was going north and south. So north and south is around the poles. But why was he wrong? So I'm going to create a Dropbox or a homework box for you to submit your answers. Now, you will not be penalized if you get it wrong, but I will let you earn some points on your first exam if you get it correct. All right, so let's take a look at the challenge today. Let's pretend that you are talking about the shape of the earth with 5th and 6th graders. Which one would be the best model of the earth for you to bring in? A beach ball or a grapefruit? And why? Now this is one that this will be worth 5 points. All you need to do is explain your reasoning to me. Why do you think a beach ball or a grapefruit would be a better model for the shape of the earth with 5th and 6th grade students? And that concludes the lecture for today. If you have any questions, please don't hesitate to email me. And remember that Wednesday is not face-to-face for anybody. And I know a lot of you, I think there are 7, have COVID tests that haven't come back. There is somebody who is sick, and there's also somebody who has to self-quarantine. So please remember, Wednesday is remote for everybody. And you guys have a wonderful week, and I will see you soon. Thank you.